In this lecture, we will discuss about noisy channels. The stop and wait protocol gives us an idea of how to add flow control to its predecessor. Noiseless channels are non-existent. We can ignore the error or we need to add error control to our protocols. We discuss three protocols in this lecture that use error control. The first protocol is stop and wait automatic repeat request protocol. Our first protocol called stop and wait automatic repeat request adds a simple error control mechanism to the stop and wait protocol. Let us see how this protocol detects and corrects errors. To detect and correct corrupted frames, we need to add redundancy bits to our data frame. When the frame arrives at the receiver side, it is checked and it is corrupted. Means it is checked and if it is corrupted, it is silently discarded. The detection of errors in this protocol is manifested by the silence of the receiver. Lost frames are more difficult to handle than corrupted ones. To detect and correct corrupted frames, we need to add redundancy bits to our data frame. When the frame arrives at the receiver side, it is checked and if it is corrupted, it is silently discarded. The detection of errors in this protocol is manifested by the silence of the receiver. Lost frames are more difficult to handle than corrupted ones. In our previous protocols, there was no way to identify a frame. The received frame could be the correct one or a duplicate or a frame out of order. The solution is to number the frames. When the receiver receives a data frame that is out of order, this means that frames were either lost or duplicated. The thing is, the completed and lost frames need to be resent. If the receiver does not respond when there is an error, how can the sender know which frame to resend? To remedy this problem, the sender keeps a copy of the sent frame. At the same time, it starts a timer. If the timer expires and there is no acknowledgement for the sent frame, the frame is resent, the copy is held, and the timer is restarted. Since the protocol uses the stop and wait mechanism, there is only one specific frame that needs an acknowledgement, even though several copies of the same frame can be in the network. Since an acknowledgement frame can also be corrupted and lost, it too needs redundancy bits and a sequence number. The acknowledgement frame for this protocol has a sequence number field. In this protocol, the sender simply discards a corrupted acknowledgement frame or ignores an out of order one. Let us see what you mean by sequence numbers. As we discussed, the protocol specifies that frames need to be numbered. This is done by using sequence numbers. A field is added to the data frame to hold the sequence number of that frame. One important consideration is the range of the sequence numbers. Since we want to minimize the frame size, we look for the smallest range that provides unambiguous communication. The sequence number of course can wrap around. For example, if we decide that the field is m bits long, the sequence numbers start from 0, go to 2 power m minus 1 and then are repeated. Let us reason out the range of sequence numbers as we need. Assume we have used x as a sequence number. We only need to use x plus 1 after that. There is no need for x plus 2. To show this, assume that the sender has sent the frame numbered x. Three things can happen. First thing is, the frame arrives safe and sound at the receiver side. The receiver sends an acknowledgement. The acknowledgement arrives at the sender side, causing the sender to send the next frame numbered x plus 1. Second thing, the frame arrives safe and sound at the receiver side. The receiver sends an acknowledgement, but the acknowledgement is corrupted or lost. The sender resends the frame numbered x after the timeout. Note that the frame here is a duplicate. The receiver can recognize this fact because it expressed frame x plus 1, but frame x was received. Last thing is, the frame is corrupted or never arrives at the receiver side. The sender resends the frame numbered X after the timeout. We can see that there is a need for sequence numbers X and X plus 1 because the receiver needs to distinguish between case 1 and case 2, but there is no need for a frame to be numbered X plus 2. In case 1, the frame can be numbered X again because frames X and X plus 1 are acknowledged and there is no ambiguity at either side. In case 2 and case 3, the new frame is X plus 1, not X plus 2. If only X and X plus 1 are needed, we can let X equal to 0 and X plus 1 equal to 1. This means that sequence is 0, 1, 0, 1, 0 and so on. Is this pattern familiar? This is modulo 2 arithmetic. Since the sequence numbers must be suitable for both data frames and ACK frames. ACK means acknowledgement. We use this convention. The acknowledgement numbers always announce the sequence number of the next frame expected by the receiver. For example, if frame 0 has arrived safe and sound, the receiver sends an acknowledgement frame with acknowledgement 1, meaning frame 1 is expected next. If frame 1 has arrived safe and sound, the receiver sends an acknowledgement frame with acknowledgement 0, meaning that frame 0 is expected. At final, you must remember one thing. In stop and wait ARQ protocol, the acknowledgement number always announces in modulo 2 arithmetic the sequence number of next frame expected. In stop and wait ARQ, the acknowledgement number always announces in modulo 2 arithmetic the sequence number of the next frame expected. Let us see the design of the stop and wait ARQ protocol. You just observe on the screen. This is the design of the stop and wait ARQ protocol. The figure 10 shows the design of the stop and wait ARQ protocol. The sending device keeps a copy of the last frame transmitted until it receives an acknowledgement for that frame. A data frame uses a sequence number and acknowledgement frame uses an ACK num. That means acknowledgement number. The sender has a control variable which we call SN here. That means sender next frame to send. That holds the sequence number for the next frame to be sent 0 or 1. The receiver has a control variable which we call RN, which means receiver, next frame expected. That holds the number of the next frame expected. When a frame is sent, the value of SN is incremented. Incremented means how it would be incremented means by modulo 2, which means if it is 0, it becomes 1 and vice versa. When a frame is received, the value of Rn is incremented. How it would be incremented means by modulo 2 operation, which means if it is 0, it becomes 1 and vice versa. 3 events can happen at the sender side. 1 event can happen at the receiver side. Variable Sn points to the slot that matches the sequence number of the frame that has been sent but not acknowledged. Rn points to the slot that matches the sequence number of the expected frame. Let us see algorithm. Algorithm 5, sender side algorithm for stop and wait ARQ. You just have a glance on the screen. You will understand easily. Let's see the analysis of this algorithm. We first notice the presence of Sn, the sequence number of the next frame to be sent. This variable is initialized once in the line 1, but it is incremented every time a frame is sent in line 13. In preparation for the next frame, however, since this is modulo 2 arithmetic, the sequence numbers are 0, 1, 0, 1 and so on. Note that the processes in the first event, which are send frame, store frame, use an SN defining the frame sent out. We need at least one buffer to hold this frame until we are sure that it is received safe and sound. In the line 10 shows that before the frame is sent, it is stored. The copy is used for resending a corrupt or last frame. We are still using the can send variable to prevent the network layer from making a request before the previous frame is received. Safe and sound. If the frame is not corrupted and the acknowledgement number of the acknowledgement frame matches the sequence number of the next frame to send, we stop the timer and pursue the copy of the data frame we saved. Otherwise, we just ignore this event and wait for the next event to happen. After each frame is sent, a timer is started. When the timer expires, you can see this in the line number 28, the frame is resent and the timer is restarted. Let us see the algorithm 6, a receiver side algorithm for stop and wait ARQ protocol. We will see the analysis on this algorithm at receiver side. This is noticeably different from algorithm 4. First, all arrived data frames that are corrupted are ignored. If the sequence number of the frame is the one that is expected, which means Rn, the frame is accepted, the data are delivered to the network layer and the value of Rn is incremented. However, there is one sub point here. Even if the sequence number of the data frame does not match the next frame expected, an acknowledgement is sent to the sender. This acknowledgement, however, just reconfirms the previous acknowledgement instead of confirming the frame received. This is done because the receiver assumes that the previous acknowledgement might have been lost. The receiver is sending a duplicate frame. The recent acknowledgement may solve the problem before the timeout does it. You just look at the diagram. Whatever the sender side algorithm is there, that algorithm they had shown in this diagram, how it is moving one function to another function and how it is sending the acknowledgement and how it is receiving the acknowledgement. How it is sending the acknowledgement and how it is receiving the acknowledgement, you can see in this diagram. Okay, we just have a glance on this diagram. You can easily understand how that sender side algorithm works. And you see here, this is a receiver side algorithm. How the receiver side algorithm it is working, that you can easily understand if you have a glance on this slide. Let us see one example. Figure 11 shows an example of stop and wait ARQ. Frame A is sent and acknowledged. Frame 1 is lost and resent after the timeout. The resented frame 1 is acknowledged and the timer stops. Frame A is sent and acknowledged, but the acknowledgement is lost. The sender has no idea if the frame or the acknowledgement is lost. So after the timeout, it resends frame 0 which is acknowledged. See, in this there is a efficiency. You just look at here, this efficiency. The stop and wait ARQ discussed in the previous section is very inefficient if our channel is thick and long. By thick, we mean that our channel has a large bandwidth. By long, we mean the round trip delay is long. The product of these two is called the bandwidth delay product. We can think of the channel as a pipe. The bandwidth delay product then is the volume of the pipe in these bits. See, the bandwidth delay product then is the volume of the pipe in bits. The pipe is always there. If we do not use it, we are inefficient. The bandwidth delay product is a measure of the number of bits we can send out of our system while waiting for news from the receiver. So this is the procedure it is going to follow here. So time limit is here, it has taken 0, means a first packet bit it is transmitted and it is going to take acknowledgement here, and within this time, if it is not able to receive the acknowledgement, again within this time it will be resent. Let us take another example. Assume that in a stop and wait ARQ system, the bandwidth of the line is 1 Mbps and one bit takes 20 milliseconds to make a round trip. What is the bandwidth delay product? If the system data frames are 1000 bits in length, what is the utilization percentage of the link? Let us see the solution. The bandwidth delay product is 1 into 10 power 6 into 20 into 10 power minus 3 equal to 20,000 bits. See this diagram. The system can send 20,000 bits during the time it takes for the data to go from the sender to the receiver and then back again. However, the system sends only 1000 bits. We can say that the link utilization is only 1000 per 20,000 or 5%. For this reason, for a link with a high bandwidth or long delay, the use of stop and wait ARQ wastes the capacity of the link. Let us see another example. What is the utilization percentage of the link in example 4? If you have a protocol that can send up to 15 frames before stopping and worrying about the acknowledgements, the solution is the bandwidth delay product is still 20,000 bits. The system can send up to 15 frames or 15,000 bits during a round trip. This means the utilization is 15,000 per 20,000 or 75%. Of course, if there are damaged frames, the utilization percentage is much less because frames have to be resent.